So, welcome to this presentation, Fatigue Strength Improvement of Bridges. The recording is now started, and those participating in the recording will not be shown in the recording unless they ask questions at the end. And we will open up for questions when Poja is finishing his presentation. So, the floor is yours, Poja.
Thank you, Kjersti. Welcome to this presentation, which is based on my research, which I have done mainly up to my licentiate, which is a project within the E39 project, PhD projects. So I am a PhD student, industrial, from WSP, working here at Chalmers with my supervisor, Mohammad Al-Emrani, and as you could see in the title, we are looking at the fatigue strength improvement of steel bridges, and which can result in material savings and more efficient bridge designs. So, a brief introduction. The question might rise, what is fatigue? Well, according to Wikipedia, fatigue is the weakening of a material caused by repeatedly applied loads. It is the progressive and localized structural damage that occurs when a material is subjected to cyclic loading. So, with other words, if you ever have tried to bend a paper clipper, that is fatigue failure. And this happens, the same phenomenon in bridges, but of course much lower loads and for millions of cycles. This failure mode is what determines the material consumption and the lifetime of the most steel bridges, and it is a very dangerous type of failure, especially in old bridges and where old steel were used. The failure can be very brittle and sudden and occur after many years of operation, so you don't get any warnings. Just quick examples. So in 2013, this bridge collapsed due to fatigue. It's a bridge in the Interstate 5 in Washington. A very similar type of bridge collapsed a couple of years earlier with almost the same type of bridge, and this was also due to fatigue in Interstate 35 in Minnesota. So the outline of my presentation will first be try to be a quick background on fatigue in bridges, how we can improve them by different post-weld treatments, and then I present specifically one of these treatments, which is called HFMI, which stands for High Frequency Mechanical Impact Treatment. And then I will present you the aims and objectives that I had in my licentiate, which I have fulfilled, and very shortly about what I continue working on. And how I fulfilled these aims and objectives are presented in the results in terms of case studies I performed on calculations on bridges that exist and how we could save material with HFMI treatment. Something about the thickness effect, which I will come back to, which is a phenomenon in fatigue. And then the experimental results that we performed here at Chalmers, which will show very interesting things that you should anticipate. So background, fatigue in bridges in general. Bridges are designed with regards to the different design limits, which more or less is different criteria. And these criteria can be divided into ultimate limit state, which is the first one. This is all the criteria regarding the collapse of the bridge or the immediate failure of the bridge due to very extreme loads. Then you have serviceability limit states. It can be usability of the bridge. It should be able to operate in a comfortable way for the users. It should not deflect too much. So one criteria is more or less deflection of the bridge. In pedestrian bridges, it can be vibrations, etc. And then you have the fatigue limit state, which also concerns the total failure of the bridge, but this occurs during many years and for a regular loading of the bridge, so it doesn't have to do with extreme loads. Now, in many steel bridges, the fatigue is the dominant design criteria, which means it determines the amount of material that is needed. And the reason is that we have welds in our bridges, and welds are weak links. And with today's technology, we cannot avoid welds. And the reason they are weak links is because the change of geometry causes some stress concentration at some sensitive areas, which I try to show here. The reason these areas are sensitive is because also weld defects exist here, which can be very sharp, crack-like defects. So they act as local stress raisers, raising the stress even more. And finally, we have tensile residual stresses. So these are self-balancing stresses that exist inside the component or detail even before you load it. And since they are in tension, they are very detrimental for fatigue cracking and propagation and initiation of cracks. So this is why fatigue is so dominant and occurs at weldments. And one of the consequences of this is that we're trying to show it in this graph here. We have the loading over here for fatigue and the number of cycles it can endure. And what this graph tries to show is that if you don't have any weldment, if you just have a base plate, you have very high strength. If you introduce a round hole around the discontinuity, it decreases somewhat. But if you weld it with all the factors that I mentioned, it dramatically decreases the fatigue strength. And another consequence is what we see here is the fatigue strength on the y-axis and the tensile strength of the material. So what this graph shows is that if you have a sharp notch, as in the case of weldments, you have more or less no influence of material strength on the fatigue strength. This is of course bad because it doesn't allow us to use high-strength steel. It doesn't allow for modern steel materials and an optimal design of the bridge. So the material use becomes inefficient, and we cannot use high-strength steel. So some of the post-weld treatments that I will show here, the goal for them is to reduce the stress concentrations caused by the welding and also remove the weld defects. And by doing so, the aim is to become more like a non-welded notched specimen in terms of fatigue. And here we see a lot of pictures. The top one is illustrating a case of grinding method, a post-weld treatment. You see the tool and you see how the result looks like after the treatment. So we have a very round and smooth transition, which reduces the stress concentrations. In the middle one here, the goal is the same, and the result is also the same, a little bit better maybe. This is by remelting the weld. And the last one, which will be the focus of my presentation, is the HFMI treatment, which impacts this region which is sensitive and makes to some degree a smoother transition. But what I will come to is that this method, the high-frequency mechanical impact treatment, also introduces compressive residual stresses. And here we have different manufacturers of this technology, and the tools look a little bit different. All of them are handheld tools. And the research that has been done show that they give similar results in terms of degree of improvement. So they induce compressive residual stresses, which is very beneficial. It's considered to be the main benefit of this treatment. And what we see in this illustration is that before treatment, we have the red area, which is very high tensile residual stresses, and when we do the treatment, we introduce compression. The advantages compared to the other methods is that this gives the highest improvement, especially for applications such as bridge application. It is material strength dependent, so the degree of compressive residual stresses is dependent on the material strength, so we have additional benefits of using high-strength steel. And it is a very fast technique to do the treatment. It's at least as fast as welding or quicker, while the other methods can be slower. Some of the drawbacks are that these compressive residual stresses are sensitive to overloads that can occur, extreme loads that can remove the stresses, and with that also the benefits. And also the mean stress can be influencing the degree of improvement. So my aims and objectives, those that I have fulfilled in this licentiate thesis and will present the results of, are to study the benefits and limitations of using HFMI on bridges. In terms of material saving, how much improvement can you get, what criteria can be limiting, etc. And I assess the effect of plate thickness on the fatigue strength of HFMI treated specimens. And finally, I investigate experimentally the fatigue strength of these improvement technique for typical details in bridges with typical material strengths and thicknesses. And currently, I'm looking at characterizing bridge loads in conventional bridges and try to see the influence of overloads and mean stresses. So just as a beginning, I want to ask how do we save material? So I try to illustrate this in a way. So one thing is, of course, that we want to utilize the strength as much as possible. Can sound a little bit abstract, but I will make an illustration. And we want to use high-strength steel. So if you look at this chart here, it describes the utilization of different design states, limit states, for a typical bridge. So this is not far from reality, which says that in a normal case, you have fatigue limit state being utilized to 100%. With other words, it is determining the dimensions of the bridge. This makes the other two design limit states be lower or competing. But for instance, in railway bridges, this is very common that the strength against extreme loads and direct failure, which is the ultimate limit state, is not utilized fully. And also the limits you have on the deflection is not, we are not near that. So this is considered to be an inefficient design, according to us. So what you can do then, I will show the effect of post-weld treatment. So let's assume that we treat the fatigue critical details in this bridge. Suddenly, we don't utilize the fatigue strength anymore. And this means that the next design limit state, which is governing, is the ULS, and we have 30% left to optimize, which implies that we can actually reduce the thicknesses of our steel plates in the bridge and make it more optimal. So let's say we decrease the thicknesses. All design limit states are now utilized a little bit more, and the ultimate limit state is governing. What is good now is that we can actually use high strength steel. And let's assume that we increase the steel grade, then the ultimate limit state is decreased. And we can continue like this until, for instance, the deflections are becoming governing. So to sum up this, the intention is, the goal is to go from the blue bars where you have a normal design to a desired design which is more optimal. But there are things that can be limiting. So in terms of fatigue, for instance, these are 4 details that are very common in bridge girders in conventional bridges. And detail A, B, and C are all very suitable for performing HFMI treatment on. However, the longitudinal welds which go along the bridge, which can be several tens of or hundreds of meters, these welds are not suitable for HFMI treatment. So since these welds are subjected to the same stress levels as the other details here, the strength of this detail will be governing. So this will be limiting, actually. For the fatigue limit state. For the serviceability limit state, of course, the deflection is limiting, because using high strength steel does not decrease the deflections. And of course, you can have vibrations and other phenomena, which I have not considered here. In the ultimate limit state, of course, increasing the material strength will be very influential, but you have instability phenomena, which can be limiting also. And additional limits of this improvement technique is the mean stress, of course, and the overloads from variable amplitude loading. So let's go to the case studies I did. So this is a bridge in Gothenburg, which was designed with these utilizations, as you see. So it was actually fatigue that was determining the dimensions. Since this was a railway bridge and the conditions were quite strict, the deflection was also utilized quite high, but not the ultimate strength, actually. So by only performing calculations, so this is only theoretical, I used the same calculations that were used to design the bridges and just improved the fatigue strength. We could save 17% steel in these main girders, so that corresponded to 30 tons. And we didn't even have to use high strength steel, because by reducing the bridge with 17% of steel, we actually came up to the deflection limit. So there was no meaning of using higher strength steel. And in this kind of bridge, we see that the mean stresses are very low, because the bridge itself is very light, while the traffic, which is trains, is very high. This results actually in a very low mean stress, which is very suitable for this improvement technique. This is a composite steel and concrete bridge, which is not a railway bridge, it's a road bridge. And here we can see that actually fatigue and the ultimate limit state were competing. They were both very high. However, the deflections were very low. In this case, we could increase the yield strength to theoretical yield strength of 620, which resulted in 22% of material saving in this bridge. Since this bridge was very small, this was only corresponding to 5.4 tons. And we also could see that it was very high mean stresses in this bridge. So it might not be very efficient in actuality if you perform the HFMI treatment in the workshop. However, some studies show that even for high mean stresses, if you perform the treatment after the self-weight is put on, it cancels out, so the benefits become the same again. So that's why we did this anyway. And here we have a similar type of bridge, however, spanning over five spans instead of the previous one, which was simply supported. Here we can see the fatigue was actually quite highly governed, utilized. And in this case, we could save 23% in the main steel girders, which corresponded to 30 tons. And we could go up to a steel grade of 460. Also here, the mean stresses were high. So this 460 here, in combination with a parametric study I did, which I have not shown here, for railway bridges, it shows that 460 seems to be a quite suitable material strength when we optimize our bridges. So some of the conclusions is that you can generally save more or less 20% in the main load carrying members. The S460 considered appropriate steel grade after optimization, and thinner plates, when you optimize your bridge, thinner plates are also better in fatigue, so there's a double effect there. And also in terms of working cost and welding cost, you can save considerable amounts, especially in welds called butt welds. Then railway bridges have low mean stress if they are purely made of steel, and HFMI performs well, while on composite bridges where you have concrete, HFMI might not be very good unless you perform it after the self-weight is applied. Now we go on to the results of one of my two papers included in the licentiate. So it's about the thickness effect. And what is the thickness effect? It is a weakening of the fatigue strength when we increase the main plate thickness. And I will not go into more details on how this works. However, I will present some of the results. So I gathered 600 fatigue results from the literature on HFMI treated details. And for this type of detail, I could then evaluate the fatigue strength in terms of or as a function of the thickness of this main plate. This weldment is called butt weld, and we can see this value is a measure of how the severe the thickness effect is. So what we can see is that it was very weak, actually, because if you compare to what codes say for non-treated details of this kind, we have this kind of slope, which illustrates how much you lose in strength with increasing thickness. And this actually is a considerable degradation when you consider, for instance, the number of cycles you can endure. So performing HFMI on these details actually more or less removes the thickness effect. For this type of detail, we can compare to non-treated and see that, okay, there is a thickness effect, but it becomes actually weaker. And then this is the last detail I investigated, and surprisingly, there is no thickness effect. Actually, there is a reverse thickness effect. So increasing the plate thickness actually seems to increase the fatigue strength. And for instance, in IIW, International Institute of Welding recommendations, they say that you should perform such a reduction of the strength, which doesn't seem to actually reflect the reality. So another way to illustrate this, we have this black curve representing the fatigue strength as a function of thickness for non-treated welds. Then we have the red curve, which is new guidelines, recommendations for HFMI treatment. So what we see is that the fatigue strength is increased. However, the thickness effect is parallel to this, so more or less the same. And my gathered data showed actually such a curve. So the strength is higher than what the guideline says, and the thickness effect is much weaker also. For this detail, we have a similar thing. However, what is more clear here is that the fatigue strength is from experiments much higher than both non-treated or as welded cases, and also what is recommended for HFMI treatment. While the degradation rate is almost the same. However, a little bit weaker. For this detail, it seems that like the strength is represented well in the code if you compare the red line and the blue line. However, the thickness effect is different. So we have a more beneficial reality than the codes. And I should also say that the result curves, which are the blue curves here, they are representing characteristic strength. So 95% of the gathered data lie above these lines. So some conclusions: the thickness effect becomes weaker with HFMI treatment. So we can say that for this detail, almost no thickness effect. For this detail, the thickness effect becomes milder. And for this one, we don't even have a bad thickness effect, actually a reverse one. So what the codes say that we should reduce the strength is not appropriate here. And also we can say that there's an extra benefit of optimizing a bridge with thinner plates, because HFMI treatment performs even better for thicker plates. This is one conclusion. So to the experiments, which I find very interesting, is what you see here is the specimens that we manufactured. We manufactured many of these and tested more than 50 of these plates. So this should represent a lower or a flange in a steel bridge, with the attachment coming vertically for vertical stiffening. And we performed several investigations. We looked at the microstructure of these specimens at different regions. We looked at how does the HFMI treatment change the geometry at the sensitive area. So for this upper one, we have a non-treated, or also called as welded case, and we can see that when we treat it, we induce these groove of the treatment trail. So we investigated that, and we also looked at how the residual stresses look like after and before the treatment. But I will not discuss this more. I will go directly to the fatigue strength results. So what we tested was two different steel grades, the conventional 355, which is used today in bridges, and also the a bit higher one of 460. And the main plate, we chose to look at 40 and 60 millimeters, which can be the relevant cases in bridges. We took those specimens that I showed you, we put them on two supports and tested them in bending with low mean stress and constant amplitude, which is the most conventional way of testing the fatigue strength of weldments. And for the thinner plates, we can see here what the results are. So what you have in the blue line is the lower strength steel, the 355 steel, and the upper one is the 460 steel. And of course, this is the thinner plates. And the improvement is dramatic, actually. So let's consider a loading of 200 megapascal. That would, in a regular case, correspond to approximately 100,000 cycles before the detail fails. While if we use HFMI treatment with a steel grade of 355, that corresponds to 1 million suddenly. And if we go on to the 460 steel, that is suddenly more than 3 million cycles before failure. So more than 3 million cycles compared to more than between 150,000. It's a dramatic improvement. And the improvement is similar actually for the thicker plates, actually very similar. So again, we don't see a very clear thickness effect in our experiments. And the improvement is very high. So the conclusions of my presentation is that maybe not in all bridges, types of bridges, for instance, maybe not in truss bridges, but in conventional bridges, you can save at least 20% material saving in the main beams. And this also applies for conventional bridges. We think that 460 is suitable. However, in other types of bridges, I've seen examples where 690 have been used in truss bridges, in combination with HFMI, of course. And we know that the mean stress effects and the longitudinal welds that cannot be treated, they are limiting. The thickness effect is weaker, then as well dead, and the fatigue strength improvement is significant according to experiments. So that is the conclusions, and for future research, as I mentioned, I will look at variable amplitude loading. So what you see here is a simulation of actual traffic measurements simulated by driving on influence lines of bridges. And we want to investigate how these peak loads influence the fatigue strength and the mean stresses that are there. And that is all. Thank you for listening.
Thank you. And then there's open for questions, if any one of you have one.
Yes, I have a question, if I may.
Yes.
Yes, go ahead.
My name is Kjell Belsvik. I'm working with the bridge of Bjørnafjorden. And we are also discussing steel qualities, as you have studied here. For the time being, we have landed on our 420 quality. But we can see that fatigue is a dimensioning factor for us.
Interesting.
Yes, it's very interesting, and also the weight saving that you indicate also applies to the buoyancy need that we have.
Yes.
So if we can save a ton in the main girder, we can also save a ton in need for buoyancy.
Exactly.
So we have a double effect on floating bridges for this specific topic. But the question is actually, when we say weight, we add more work when we do this treatment.
That's correct.
Do we have any indication of the increased cost for man hours and equipment when we do this treatment compared to the saved weight that we gain?
Compared to what the last?
Yes, so we gain some weight when we reduce the sizes,
Yes.
dimensions, and that means that we also can save some costs when it comes to material building.
Yeah.
But we add some extra work when we do the treatment.
Yes, of course. And
do we know something about the cost of the treatment?
The cost of treatment can be very different because this is a young technique and developing. A lot of companies are growing and making their a lot of competition. So we have had very different values on what it can cost. But there are opportunities that you can acquire this. For instance, the contractor can do it, acquire it, and because it's a very easy procedure and it doesn't require very high training costs. So, and it's very, very case sensitive. For instance, one of my case studies that I looked at, there were very few details that required improvement in order for the whole bridge span to be optimized, while one of the other case studies, there were a lot of details that required treatment. So, yeah, that's more or less what I know and what I can say. But the overall impression is that the treatment cost may be negligible compared to the total benefit.
Yes, and do this equipment require more space? Do we need to design space for these details to be treated?
Well, of course, to do this, you mean the geometry of the treatment equipment itself?
Yeah.
If it requires space. Well, this is also very depending on the technology that you use. So we have looked at some of them. It's more or less only the tool that you hold with your hand, and you have to apply air pressure to it, which can be a general air pressure from whichever equipment that you have. It has to be at least 6 bars or something like that. While there are others that require some more space. But in the context of bridges, they are can be considered portable.
Yeah.
I would say.
If I can just add a little bit on the questions that Kjell Håvard has asked. For these floating bridges, we are talking about a steel box girder and not open truss or a beam. That's why the space could be critical, especially when it comes to the corners of this box girder. But I guess that would be something that will have to be looked into. But
of course, but still the dimensions you're talking about are the box is maybe 2, 3, 4 meters high or something.
Yeah, I mean, it would be easy to get people into the boxes, but the question is to get the people and the equipment out to the very fine edges. If you consider, say, a suspension bridge, you can see that it has a pointy
Exactly.
end. And this is also one of the points where it could be sensitive to fatigue.
Yeah.
But my question, this is a technique that you apply either before you put the bridge in place, or you apply the self-load, or either right after you have applied the self-load.
Exactly.
So it's not something that if you look to the previous the method, that you can kind of grind down the toe of the weld. That is something that you do, say, after a few years. Could it be something that you can use to kind of fix a problem that you see occur?
Yes, so you mean more or less using this technique for refurbishment or reparation?
Yeah.
Yes, this is actually something that is going on or research at our department. It is not something I have looked at, but I have come over several articles where they have investigated this, and it looks actually very promising. In many articles, they say that this treatment, if you can assure that you don't have any cracks in your current weld, which has been operated for several years, if you can do that, then you can perform this treatment, and it more or less restores the strength of the weld and removes any damage, so the damage becomes zero. It is also very case specific. So if you want to repair a weld that already you can see there's a crack, but it's a shallow crack, then you might need to first grind away that cracked, the damaged area, and then you can perform this treatment afterwards also, which also have been researched on and looks promising.
Thank you.
Okay, do we have any more questions?
I can add another question. If you were to say improve or use this technique on a weld, how long time will you spend on, say, 1 meter?
Yeah, I have a figure on that actually, which I am not sure what it was. Well, could it have been 200 to 300 millimeters per minute or something like that? Or was it? Yeah. I can actually see if I can find that very quickly, but you can always, as a safe side estimation, say that it's as quick as the welding. And I have actually a figure here because I measured it while we did this treatment. So yes, 200 to 300 millimeters per minute.
Thank you.
Could I also ask a question? Since I'm always interested in the money part of the project, that's sort of my type of questions. But if we could use these techniques that you are working on, how much money would that save on a bridge that would be, say, 3 kilometers long?
I think, which I was surprised that fatigue was so governing. I think if fatigue is governing and the details are suitable for this treatment and they are accessible, etc., I think in these cases the cost saving can be much more considerable than the conventional bridges I have looked at. Because in the conventional bridges, the raw material cost saving is not so much, because steel is actually very cheap, while we think that in conventional bridges the welding costs that you can be very much reduced are the most considerable part. And then you have also, of course, environmental and societal aspects, which in my opinion you should convert into costs, which also is already very high for the conventional bridges if you save 30 tons. And in a long span bridge, I think I have not experience in designing long span bridges, but I think there's a snowball effect in saving material in all parts, maybe in cables or in pylons or in transports of much lighter bridge segments, etc. So I cannot say any values, but I think they can be very high.
I can add some information about this. As if we take a estimate on the Bjørnafjorden Bridge, which is about 60,000 tons of steel in the girder, and if we say that only the top flange of the bridge box is reduced due to fatigue challenges, and the reduction is say 10% only, the cost saving can be around 150 million Norwegian crowns. That's an estimate.
Interesting.
Yeah. Thank you, Kjell Håvard.
And Tom Norbeck, when you say 150 million kroner, what would the total be?
For this bridge, this is the total saving for this bridge, as long as if we estimate 60,000 tons of the bridge girder steel.
Yeah, but when it's 150 million in savings, I'm just curious about what is the total. How many percent do we save on this?
That would be approximately 1% of the
okay.
The total cost, including owner's cost, etc.
Okay, I see.
Yeah, and also this is only a saving that applies to the top flange of the bridge girder. The bottom flange will not be subjected to fatigue in the same way, because the traffic is on the top side. So this estimate was I take the total weight, divide it with half. So half of the bridge girder is subjected to traffic, and as indicated, maybe 17 to 20% savings. Well, to be conservative, maybe 10%, as we see the bridge, the top side of the bridge girder is not totally subjected to fatigue either, as we have some path of pedestrians area and areas that are not subjected to traffic on the top flange as well. Yeah.
this is a very interesting numbers and figures, but of course everything is case specific, so you would have to investigate whether these details are suitable for treatment and not, etc.
Yes, as we need to have a bridge with standardized sizes, stiffeners and so on, and also standard details, the possibilities to reduce the sizes is possible to do in a general basis, and also then we can use this method that we have seen improves the fatigue strength in the needed areas only.
Yes, exactly.
Well, it's very interesting to hear about this. Thank you very much.
Thank you.
Okay, do we have any more questions? No? I think some of you should follow up on the exchange of knowledge between Bjørnafjord and your project, Poja. So you should stay in touch. Before we end this session.
Since I didn't know which persons that asked me, please send me an email and we can continue our discussions. It would be very interesting. I've been interested in these questions for a long time.
I can challenge Matthias to make a meeting to meet a selected group of persons from Bjørnafjord at least.
Very good.
Yeah.
Okay. Okay, then I will just remind everyone that on April 6th we will have a new presentation. Then it will be smart warming of bridge decks, which is the topic. And also from April and outwards, we will have a lot more presentations concerning bridges. So now we're changing the topic a little bit from sustainability to bridges from after Easter. And then I think I will say thank you for the presentation today. And it was a very good and interesting presentation, and the discussion afterwards also showed that this is very useful for the Norwegian Public Roads Administration. And by that, I would like to wish everyone a happy Easter.
Thank you. Same to you.
Thank you. Happy Easter to you too.
Okay.
Bye-bye.